The electrolytes can conduct electricity only in the molten or aqueous state. Its resistance is directly proportional to the length of the material and inversely proportional to the area of cross section. So this conductivity cell consists of two platinum electrodes coated with platinum black. So according to Wheatstone principle, we know that R2 by R4 will be equal to R1 by R3. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with session 5 of the chapter Electrochemistry. So in the last class we discussed the product of electrolysis, and in today's class we are going to discuss conductivity of solution and how we can determine the conductivity of solution. Okay, so before that we have to start with what are conductors. So you might be familiar with metallic conductors, right? Generally the term conductors you might be familiar with. So simple definition, conductors are the substances which can conduct electricity, right? It will allow the passage of electricity through it. So we are going to see the different types of conductors here. What we are going to focus about is electrolytic conductors. Okay, so let's see. The substances which allow the passage of electricity through them are known as conductors. So conductors of electricity are further classified into metallic conductors. It means that metals which conduct electricity, right? So electrical conductance through metals are called as metallic conductors. It is due to the movement of electrons. So you have to remember this point, that is why metals are able to conduct electricity, because of the presence of electrons. So we have already studied movement of electrons is in this direction. Electricity will be generated in the opposite direction. So this already you have studied in your lower classes itself. So that is metallic conductors. Now it depends upon the nature and structure of the material, the number of valence electrons per atom and the temperature. So these are the factors in which the metallic conductance depend upon. That is how many number of electrons are present and what is the nature and the structure of the metal as well as the temperature. Now moving on to the next one, that is electrolytic conductor, which is of our importance in this chapter, right? So the conductance of electricity by ions present in the solution is called electrolytic or ionic conductance. So in metals, the presence of electrons is the one which helps in the passage of electricity, but in the case of electrolytic conductance, what is electrolytic conductance? It is happening due to the presence of ions. For example, I can take sodium chloride, which is an example of an electrolyte, right? So we already know what is an electrolyte. So sodium chloride is an example of an electrolyte. In its solid state, it will not conduct electricity. But if sodium chloride, if we have taken it in aqueous state, that means in the presence of water, what is going to happen? You will have Na plus and Cl minus ions will be there. Yes or no? Na plus and Cl minus ions will be there. So due to the presence of these ions, it will conduct electricity. So that is called as electrolytic conductors, right? Now this ability is rendered by ions that are present in the solution due to the dissociation of electrolyte. So this NaCl, when it is present in water, that is in aqueous state, it will dissociate into Na plus and Cl minus ions. Because of these ions, conductance will happen. The electrolytes can conduct electricity only in the molten or aqueous state and not in any solid form. So this you have to remember. Sodium chloride, potassium chloride, let it be any salt as such. If you are taking it in the solid state, it is not going to conduct electricity. Only in the molten or aqueous state, it is going to conduct electricity. Right. Now, the electrolytic conductance depends upon the nature of electrolyte. What kind of electrolyte we are taking. Right. Now, the size of ions and their solvation. Okay, size of ions and their solvation. Solvation means how easily it is getting dissolved in water. The next one is nature of the solvent and their viscosity. What is that we are using to dissolve or dilute the particular substance? Now, the concentration of the electrolyte and temperature. So, these are the various factors on which the electrolytic conductance depends. So, I hope this is clear for you what is electrolytic conductors, right? It is happening due to the presence of ions. Fine. Now, moving on to insulators and semiconductors. Insulators are substances which do not allow the passage of electricity through them. They have very low conductivity. Very low conductivity because they do not conduct electricity. Now, semiconductors, they have conductivity in between that of conductors and insulators. Now, moving on to the next part. we are going to see how we can measure conductivity. Right. So what we are focusing here is, as I told you, electrolytic conductance and conductivity. That is, if I have an electrolyte with me, right, we are talking about electrolysis, right? So electrolysis means electrolyte should be present. So we are going to determine how we can measure the conductivity of an electrolyte. So to understand the terms conductivity and conductivity of an electrolyte, we need to know what is conductance, right? What is conductivity? So before that, we have to start with what is resistance and resistivity. So all of this you have already studied in your lower classes. So the first topic is resistance. The tendency of a material to stop the flow of current is known as resistance. That means it resists or opposes the flow of current, right? Resistance of an object is directly proportional to the length and inversely proportional to the area of cross section A. So we already know this equation, that is resistance is directly proportional to the length of the material and inversely proportional to the area of cross section. So you have a proportionality here. To remove that, we have to introduce a constant. The constant we are introducing here is called as rho, which is what? Which is called as resistivity, right? So R is equal to rho L by A, and this rho is called as resistivity. Right. Now, resistivity of a substance is equal to the resistance when it is 1 meter long and the area of cross section is 1 meter square. So, we have the equation R is equal to rho L by A. So, how you can define resistivity? It will be exactly equal to the resistance. Right. Resistivity will be equal to resistance when the length of the material is 1 meter and area of cross section is 1 meter square. So what happens? R will be equal to rho. Yes or no? So that will be the definition. Now the unit of it is ohm meter. So you already know that the unit of resistance is ohm. So the unit of resistivity will be ohm meter. So how you are getting this? By rearranging this equation, you have rho is equal to RA by L. Right. So what is the unit of resistance? You have ohm. Yes or no? And area is meter square and length you have meter. This meter and meter square get cancelled. You have ohm meter, which is the unit of resistivity. So I hope resistance and resistivity is clear. Moving on to conductance. So what is conductance? Conductance is the inverse of resistance. So it's a symbol we use is G, which is inverse of resistance. Okay, 1 by R gives you G value. So what will be the equation? We know that the equation for R is rho L by A. Then G will be inverse of R. That means this equation will be the inverse of that. So you will get it as A by rho L. I hope it is clear. So that is conductance. The unit of conductance is Siemens, represented by the symbol S. Now the next one is conductivity, which is represented by the symbol K. Okay, it is called kappa, which is represented by the symbol K. Now the inverse of resistivity is called as conductivity. Okay, so the inverse of resistance is conductance, inverse of resistivity is conductivity. I hope it is clear. Right, so inverse of resistivity is conductivity. So K is equal to G into L by A. So this K is conductivity, G is conductance, and you have L by A, where L by A is called as the cell constant represented by the symbol G star. Okay, so what is this L by A? Why it is called as a cell constant? For different cells, different substances or different electrodes we are taking, the length and area will be always a constant. So length by area, the ratio or the value of L by A will be always a constant for a particular substance. It will not change. So that is why we call this part, that is L by A, as cell constant, which is represented by the symbol G star. Okay. Now the unit is Siemens meter inverse. Okay. For conductance, the unit is Siemens. For conductivity is Siemens per meter. Okay. It can be expressed in Siemens centimeter inverse as well, meter or centimeter. So I hope this is clear. What is resistance, resistivity, conductance and conductivity. Right. Now, how do we measure conductivity? So that is what I was talking about. We need to understand the terms first. So the terms is clear to you. Now we are going to see how we can measure the conductivity of an electrolyte. So we are talking about electrolytes here. So electrolytes means, of course, it will be in the liquid state. So how can I measure the conductivity of a liquid substance? I cannot connect wires to it directly. Yes or no? right? How can I measure the resistance or resistivity, conductance or conductivity of a substance which is in liquid state? I cannot pass current directly through it. I cannot put wires into a liquid substance. So how do I measure that? The problems we are facing here is, one is passing direct current changes the composition of the solution. Whatever electrolyte we are having, if you are passing direct current through it, it will change its composition. Next one is, a solution cannot be connected to the bridge like metallic wire or a solid conductor. So if we need to find the resistance of a metal, we can, because we can connect it through wires. But we are talking about a solution here. So we cannot connect it through wires like we do in solid substances, right? So how we are going to do is using a conductivity cell, okay? So a conductivity cell is going to be like this. So you have a tube here. This is your conductivity cell, inside which you are going to take the electrolyte for whom the conductivity or the conductance you have to measure. So I hope it is clear. Now we have a solid substance which is your conductivity cell, inside which we have taken the electrolyte. Now this we can connect it through wires, yes or no? Right. So that is how we are going to measure. So this conductivity cell consists of two platinum electrodes coated with platinum black. So you have one platinum electrode here, another platinum electrode here. Now that is a setup in which inside you have your electrolyte solution for which you have to measure the conductivity. And these are the connecting wires which will be connected to the circuit. That is how you are going to measure the conductivity. How we are going to do that is what I am going to explain to you now. Now the resistance of the cell is given by R is equal to rho L by A. Right. Now R is equal to rho L by A. We already know the equation. We can calculate the resistance of the cell. So R is equal to rho L by A. Also rho we can write as the inverse of conductivity. Right. So resistivity is inverse of conductivity. So I can also write it as 1 by K into L by A. So that is the equation you have here. Now what do we know about L by A? L by A is G star. So I can write the equation as R is equal to G star by K. How come? This L by A becomes G star and this K is already here. So if I can calculate the resistance of this conductivity cell, right? If I can calculate the resistance of this conductivity cell and I already know about the cell constant of this particular cell, it is going to be always a constant. Yes, it will have a constant length and area of cross section. So if I can calculate the resistance and the cell constant value, I can calculate the conductivity. So I hope that is clear. So now what we are going to see is how we can calculate the resistance of this conductivity cell. I hope that is clear. So let's see. Once the cell constant is determined, we can use it for measuring the resistance or conductivity of any solution. So once we are measuring the cell constant, so as I told you, cell constant will be always a constant for a particular cell because the length and area of cross section will not change. Now what is the next thing we need? We need is the resistance. We got G star value, we need to find resistance so that we can calculate the value of conductivity, right? So now what we are going to do here, we are going to connect the conductivity cell in a Wheatstone bridge. Okay, so this is the setup for a Wheatstone bridge, and what you are having here, this particular R2 you can see, that is the conductivity cell that we have taken before, inside which we have the electrolyte for which we have to calculate the conductivity, right? So this is the conductivity cell. Then you have R1 here, which is a rheostat for which the value of resistance you can change. Then you have other two constant resistances here, which is R4 and R3, and in middle you have P, which is a detector, and it is connected to an oscillator, okay, which continuously provides an electricity through it. So what is happening here? You have R2, R1, R4 and R3, wherein R2 is the one which we have to calculate. Yes, as I told you, if I can find the resistance of this particular conductivity cell, I can calculate the conductivity of the electrolyte. So how can we calculate it? So in this format, using the Wheatstone bridge, we are going to calculate the resistance of this. So according to Wheatstone principle, we know that R2 by R4 will be equal to R1 by R3. That is, this divided by this will be equal to this divided by this. So what is that we have to calculate? We need R2. Right, we need R2. That is what we have to calculate. So I can just rearrange the equation and write R2 is equal to R1, R4 divided by R3. So I already know the values of R1, R4 and R3. I'm going to substitute in this equation and I'll get R2. right? So if I can calculate the resistance, I can use the previous equation and calculate the conductivity of the solution. So this particular equation is called as the Wheatstone principle, that is R2 by R1. This side, whatever resistance is present, their ratio is equal to R1 by R3. From that I got this equation, R2 is equal to R1 R4 by R3, from which I can calculate the resistance. I hope it is clear. So now I have the resistance value of my conductivity cell. I also calculated the cell constant, which is constant for this conductivity cell. Yes or no? So how can I calculate conductivity? Conductivity will be equal to G star by R. Yes or no? From the previous equation that we have got, right? From this equation, we know conductivity will be equal to G star by R. By just rearranging, this will go here, this will come here. So from this equation, you can calculate the conductivity of your electrolyte. So I hope that is clear. So this is going to be a constant value, and resistance we are calculating using a Wheatstone bridge, right? So that's for today, and in the next session we are going to discuss what is molar conductivity and a very important law called as Kohlrausch's law. So I hope the concepts that I have covered in the session is clear for you. So that's all for today. Thank you.